Hello, and welcome to the All the Stuff You Need to Know Python lecture. While you should be very familiar with Python from our prerequisites, you may not be familiar with some of the packages that we'll be using to do data science in Python. So today, I want to talk to you about those packages and give you a little tour. The three main packages we'll be using in this class are sklearn, pandas, and numpy. And while we'll cover sklearn when we start learning algorithms, I want to go over pandas and numpy today. So the first thing that I want to do is take my notebook and run the cell that has all of my import statement. Once that's done running, we're ready to use the pandas and numpy package. So let's talk about pandas first. Pandas does not stand for the bear, it stands for panel data, and it's a package in Python that allows us to use data frames. Data frames are basically a data structure that have rows and columns, where the rows represent individual observations and the columns represent features or characteristics of the data. The first way is by creating a dictionary and then turning that into a data frame. Here we have three lists. These basically represent the columns of our data frame. We have a list with the names, the ages, and the majors of three people. In order to create a dictionary, I'm going to call it 2DF because it's going to be turned into a data frame. To create a dictionary, we just use our curly brackets. Now the keys of the dictionary are going to be the names of the columns, and the values are going to be the lists that have all of the values for that column. And just note that the keys, aka the names you're giving your columns, don't have to be the same as the names of the lists. They just happen to be here. Now we can use this dictionary to create a data frame. I'm going to call my data frame df, and I'm going to set it equal to pd.dataframe. Data frame is a function from the pandas package that's going to allow us to create a data frame. PD is just the alias for pandas. Basically, it's a nickname that we can use so that we don't have to type out pandas every time we want to use a function from the pandas package. Now, inside this function, we're going to put the dictionary that we just created. So I'm going to say 2df. Now when we run this will create a data frame. So let's go ahead and look at our data frame. In a notebook, I can just type out the name of an object and it will output when I run that cell. So let's go ahead and run this. You can see that we've created a data frame and the notebook displays it as our output. But that's not the only way we can create our own data frame from scratch. Another way we can do it is using a list of lists instead of dictionaries. In this case, each list is a row in our data frame. Let's create a data frame. I'm going to call mine df2, and I'm going to use that same function, pd.dataframe. And I'm going to put my list of lists inside that. This will create a data frame, which I can then print out when I run my cell. As you can see, I've created essentially the same data frame. One difference is that I don't have column names. In a dictionary, we had keys that told us the column names. With a list of lists, we actually need to supply this argument called columns that is a list of the names of the columns. Now, when we run this, we'll get the same data frame, but it will have the appropriate column name. By the way, because this data frame is so small, we can just print the whole thing out. But if we ever want to only see the first couple of rows of a data frame, we can use the .head function in order to grab them. Because the data frame is so small, .head will return the exact same thing, because by default, it'll return the first 5 or 6 rows from the data frame. However, we can also specify the number of rows that we'd like to see. For instance, if I put a 1 here and then run this, it will only show me the first row of my data frame. Now, another way that you can load in data that I can't do here because I'm working in Google Colab is we could load it straight from our computer. This only works if you're running your notebook from your local computer instead of in Colab. So for instance, if you're using VS Code. In that case, you can use the read CSV function from pandas. All you need to provide it is a path to the file on your computer and it will load in the data for you. I'm not going to run this now because, like I said, I'm running in Colab, so this won't work here. But if you were running this notebook on your local computer, you could. Now, when we loaded a file from our computer, it was a file that already existed. We weren't creating our own data frame from scratch. And typically, that's what we're going to do. We're going to load in data that we have from elsewhere. Another really common way to do that is using the URL from GitHub. If you go to the GitHub for our class, you'll see a file called data. This file stores a lot of the data files that that we'll be using. For instance, if you scroll down, you'll see this file called penguin.csv. This is the penguin dataset that we're going to be using for the rest of this lecture. Now, we can load this dataset straight from the URL. All we have to do is click this little raw button first. This will take us to a way less pretty page, and we're going to copy the URL here. If you go back to our notebook, you can see that this is the URL that I've copied and pasted as a string into the variable URL_df. Don't forget to click that raw link before getting the URL. Now that we have the URL, we can use that pd.readcsv function to load in our data. I'm going to call this df4, and I'm going to set it equal to pd.read_csv and then URL_df. I could also have pasted the URL as a string into the function as the argument. Now let's go ahead and print out that data frame.head, and we'll see the first 10 rows. When I run this, you can see that it's going to load in my data for me, and it's going to print out the first 10 rows. The last way that we can load data is specific to Google Colab. If we're on Google Colab, it doesn't have access to the files on our computer, but we can upload files. To upload, we can click this little folder icon and then the upload button. This will open up a window that will allow us to select the file that we would like to upload. In this case, it's that penguin CSV file. Once this is uploaded, I can then load it in. I'm going to use that same read.csv function, but now I'm going to provide it a file path to my file. Now, luckily, the file path is just going to be the name of the file. Then I'm going to go ahead and print that out. And as you can see, it's loaded in my data from this little folder that I uploaded it to. So now that we know a bunch of different ways to create or to load a data frame, we might want to explore our data a little bit. The first thing we might want to do is see how many rows and columns our data frame has. So I'm going to say df4.shape. .shape is an attribute of our data frame that tells us how many rows, columns our data frame has. In this case, we have 344 rows and 9 columns. Another thing we might want to look at is the names of all of our columns. We can grab another attribute called columns that will print out all of the column names. This is also helpful if you ever need to copy and paste these. So now that we know a little bit more about the bones of our data structure, let's take a little bit more of a detailed look. First thing we might want to do is get some information about the columns we have. The columns in our data frame are going to be features, so let's explore them. There's two major methods you can use to do that. The first one is info. So I'm going to say the name of my data frame.info. When I run this, you can see that it indeed gives me information about all of my columns. For instance, this non-null column tells me how many non-missing values I have in that column. The D type tells me the type of data that that column is. For instance, here you can see all of our columns that are numbers are floats, whereas all of the columns that are strings representing categories are called objects. We can also use df4.describe. When we run this, it basically gives us summary statistics for all of our continuous variables. It'll give us metrics like the count, the mean, the median, etc. Another great way to explore your data is literally just to look at it. And typically we'll do that with the .head function that we talked about earlier. Remember, .head can take an argument about how many rows you want to see. So in this case, let's look at 12. When I run this, this will print out the first 12 rows of my data. And honestly, I can learn a lot. I can see all the different values of my columns. I can see that there's missing values, and I can get a bit of an idea for the range of values I'm working with. And now that we have some general information about our data, we might want to look into more fine-grained summary. I noticed that our data frame has information about different species of penguin. So what if I wanted to know the bill length of all of my different penguins by the species? Well, I can do that with a group by. Group by basically takes our data frame and groups it by the value of a specific column or columns. For instance, if I say the name of my data frame df4.group by, I can give it a list of all of the columns that I would like it to group by. In this case, I only want it to group by species. This will take our data frame and basically segment it into different parts, one for each of the unique species that occurs in our data frame. From this grouped data frame, I can grab any of the columns that I want to take a closer look at. For instance, let's actually look at both bill length in millimeters and bill depth in millimeters. This will grab only those two columns from our grouped data frame. Then we can use the summary function .mean. When we run all this together, what it's going to do is it's going to segment our data frame into one part per species, grab only the bill length and bill depth, and then take the mean for each of those species. For instance, we can see that Adelie penguins tend to have very short bill lengths, whereas Gen 2 penguins tend to have very short bill depth. Now I want to make a quick note about indices. When we have a data frame, we have basically row numbers associated with it. Like everything in Python, row indices start at 0. So this would be the 0th row, the row at index 1, 2, etc. This can be really useful to pull. So one way you can do that is say the name of your data frame .index. This will literally just give you a list of all of the indices that are in your data frame. And that's not very useful by itself, but where it is useful is when you want to iterate through the rows of your data frame. If I say for I in df4 print I, I'm actually going to be looping through the columns of our data frame. In Python, data frames are column first. So you can see when I run this, it's going to loop through all of the different columns. But a lot of the times, I don't want to loop through the columns. I want to loop through the rows. One way to do that is to use this df4, the name of my data frame, .index variable. You can see this is a range of values that I can then loop through. For instance, I could say print I. As you can see, this prints every single row number in order. In order to actually grab that row, I would need to say df4.iloc and then I. When I run this, you can see that it'll print out each individual row. And we'll talk more about iloc in a second. Now, while that loops through the row indices that allow us to actually grab our rows, we might want to loop through the rows themselves. For that, we can use for I, r in df4, the name of our data frame, .iter rows. And let's go ahead and print out both I and r. As you can see, when we run through this, it's going to print out both the actual index as well as the individual row. So we can use this to loop through our rows. Back to data exploration. Another thing that we might want to do with our data is check if it has missing values. In fact, we already saw that our penguin data does. In order to check, we're going to say the name of the data frame .isNull.sum. IsNull checks whether each entry is null, and sum gives you a summary for each column. When we run this, it basically gives us the name of each column and how many missing values it has. For instance, here we can see that the sex column is missing 11 entries, whereas bill length and bill depth are only missing 2. Now, there's lots of fun ways to handle missing data, but one really common way is just to remove rows that have any missing values. We want to be really careful that we're only dropping rows if they're missing values in columns we care about, but in this case, we care about all of them. So let's go ahead and drop our data. One way we can do this is by saying the name of the data frame equals the name of the data frame .drop NA, and when we run that, let's also double check that our missing values are indeed gone. When we run this, you can see that it's going to drop our data that's missing, so we no longer have any missing value. Now, another way to do the drop NA thing is to use the in place argument. In this case, we say the name of the data frame .drop NA, and then we use the argument in place equals true. This basically means that we're not creating a new data frame without missing values and reassigning it. We're actually changing the data frame in place. This does the exact same thing as this line above. You can choose whichever works best for you. Now, another thing we're going to want to do once we've dropped our missing values is reset our indices. Remember, our data frame has row indices like 0, 1, 2, 3, etc. If any of those rows were dropped, then those indices are skipped. So for instance, if we had 4 rows, we originally had index 0, 1, 2, and 3. But if we dropped the row at index 1, then now our indices are 0, 2, and 3. If we reset the indices, it will then reset so that our now 3 rows will be 0, 1, and 2. In order to do that, we just say the name of the data frame .reset index in place equals true. So dropping missing values is one of the things that we do to clean our data. Another thing we might do is create dummy variables. Dummy variables are just binary variables that indicate what category a data point is in. They're mostly useful when we have categorical variables with more than 2 categories. For instance, here I've copied and pasted some code that just simulates some data. You can see that data below here. Notice that I have a variable group that has at least 2 categories. In fact, I know it happens to be 3 because I made the data. Currently, I have one column that just has a string that represents whether something is in category A, B, or C. But maybe I don't want that. Maybe I want dummy variables. Dummy variables are going to create one column per category, and it's going to have a 1 if that row is in that category and a 0 otherwise. In order to grab these, I'm just going to create a new data frame. I'm going to call it dummies, and I'm going to set it equal to pd.get_dummies. And then I'm going to give it a couple of arguments. The first one is the data frame that I would like to use to create these dummy variables. And then I'm going to say columns equals, and then a list of any of the columns that need to be turned into dummy variables. In this case, it's only the group variable. When I'm done, I can type out the name of the data frame so that I can view it. Here you can see we have the same data frame, but now instead of having a single group column, we have 3 group columns, group A, group B, and group C. The rows have a 1 for whatever group they're in. One thing that we often do when we have dummy variables is we drop one of the categories because it's basically redundant. If we have a data point that has a 0 for A and B, we know that it must be in group C. So one of the things that we do is we typically drop the first category. So I can do that by saying drop first equals true. Now when we run this, you can see the output's exactly the same, except we've dropped that first category. And this works with multiple categorical variables. Here I have a new simulated data set that has 2 categorical variables. First we have grade, that's the grade someone got in the class, and then we have class, whether they're a freshman, sophomore, junior, or senior. And we can create dummies in the exact same way. I can say the name of a variable equals pd.get_dummies, and then the name of the data frame that I would like to use, and then the columns that I would like to create dummies for. In this case, it's 2, grade and class. When I run this, you can see that I've now created dummy variables for every category in both grade and class. If we wanted to drop the first category of each of these variables, we could use the argument drop first equals true. So far, we've been looking at things that work with all of our data frame, every row and every column. But oftentimes, we only want to look at subsets of our data. For instance, maybe we don't want all of our columns. Maybe we only want one. In that case, we can say the name of our data frame square bracket, and then give it a string indicating the name of the column that we want. For instance, species. When we run this, you can see it outputs just that single column. Another equivalent way to pull a single column is to just say the name of the data frame dot and then the name of the column. I'm just showing you this so that you recognize it. Typically, I'm going to use the other way because it works in almost all cases, whereas this only works when your columns have very neat names. Now, pulling a single column is really useful because we might want to do some calculations. For instance, we might want to know the mean bill length for the entire Penguin data set. To do that, we can say, let's grab the bill length column. This will just pull the bill length column. Then we can use the .mean method in order to grab the mean of that column. When I run this, we can tell that the average bill length is about 43.9 centimeters. We also might want to pull rows. Rows, remember, are indexed starting at 0. So if we know the index of the row, we can grab it. To do that, we're going to say the name of the data frame dot an ilog, which is a method we talked about earlier. After the ilog, we're going to put square brackets, which I know is difficult to remember. And then inside, we're going to put the index of the row that we want to grab. So if we want to grab the row at index 8, we're going to put an 8. I in ilog stands for index or integer. So if we have a number of a row, then we know we need to use ilog. When I run this, you can see that it grabs us the row at index 8. It grabs it as something called a series and then prints it out, which is a little bit ugly. If we take this same code and instead give it a list of indices, it will actually grab those rows, in this case 1 row, as a data frame. And when it prints out, it's a lot prettier. Again, same information, we're just displaying it differently. And we don't have to grab just a single row. If we use ilog with a range of values, we can grab multiple rows. For instance, I might want to grab the rows at the indices 2 through 7. When I do that, you can see that it'll return multiple rows to me. Now, iloc actually takes two arguments. So if we say df4.iloc square bracket and then 2 through 7, comma 1 through 4, this is saying grab the rows at the indices 2 through 7 and the columns at indices 1 to 4. When we run this, you can see that it grabs us our tiny little data frame. But often when we're grabbing rows, it's not that we know the indices of the rows, but we want to grab all the rows that meet some condition. For instance, let's pull all of the penguins that are from the island Torgerson. In order to do that, we're going to create a Boolean array. This is just an array of true and false values indicating whether the row is one we want to pull. I'm going to call my array Torg, and I'm going to say the name of the data frame, square bracket, island. This grabs the island column. In fact, I can print it out for you. You can see that just pulls the column that we're interested in. Then I'm going to check if that island is equal to Torgerson. This is what creates our Boolean array. Here we have an array indicating whether each row is a penguin from the island Torgerson. We can then use this in order to grab only those rows. To do that, we're going to say the name of the data frame, and then we're going to use a function called .loc. .loc is similar to iloc, but instead of taking the index of the rows and columns, it takes other things like Booleans or strings. If I say df.loc torg, remember torg is our Boolean array, this will say grab me only the rows that have true values in that array. Let's go ahead and run that. As you can see, it printed out all the rows that are penguins from the island Torgerson. Let's look at another quick example. Instead of island, let's look at species. I'm going to create a variable called a del, and it's going to be df4 square brackets species. Then I'm going to check if that species is equal to a deli. Then I'm going to use that to index my data frame by saying df4.loc square brackets, and then a del. This is going to grab me all the penguins that are Adelie penguins. And we don't just have to check categorical columns. We can also create Boolean arrays with continuous columns. I'm going to call this short boy, and I'm going to set it equal to df4 square bracket bill length mm. Got to spell length correctly. Now I'm going to check whether or not these values are less than 39 millimeters. This is going to return a Boolean array that's true only for penguins whose bill length is less than 39. I can grab all these penguins by saying df4.loc square bracket short boy. When I run this, you can see that it does exactly that. It grabs me all the penguins with short bill lengths. And often I want to check more than one condition, and I can do that by, again, creating a Boolean array for any row that meets our condition. I'm going to call this short boy 2. And the first thing I'm going to do is I'm going to open and close parentheses. You'll see why in a second. I'm going to go ahead and copy the Boolean array from the first problem. And this is our first condition. Then we're going to put an ampersand between them. This indicates that I want to check if both conditions are true. Then I'm going to open a new set of parentheses and put my second condition. My second condition is going to be df4 square bracket bill depth mm, and I'm going to check whether or not it is less than 18 millimeters. Now let's print this out. You can see that we're checking two conditions, but we're creating one Boolean array. This again is going to be true whenever our penguin meets both conditions and false otherwise. If we wanted to check whether either condition is true, we would instead use a pipe to represent or. All right, so now we have our Boolean array. We can use it to index our data frame. df4.loc square bracket short boy 2. When we print this out, this is all of the penguins that have both short bill lengths and short bill depths. And we can combine this with other things that we've done. Remember, loc takes things like Booleans, but it can also take strings. So let's say df4.loc square bracket short boy 2, comma. Remember, in loc and iloc, it's rows you want, comma, columns you want. So I'm going to put body mass in grams, and this says grab the rows that are in short boy 2, grab the rows that have short bill lengths and bill depth, and then grab the column body mass. I can then use the .mean method, and when I run this, it's going to grab my subset of penguins, grab the body mass column, and then take the mean of it. We can see that for our short-billed boys, their mean body weight is about 3,326 grams. And again, if I wanted to be more inclusive and include penguins that have short bill lengths or short bill depths, I would basically use the same process, but use a pipe instead of an ampersand. Now, we've talked about how to grab rows based on a condition. What about columns? Columns all have data types, and it can be sometimes useful to grab all of the columns with similar or the same data type. For instance, when we said df4.info, that gave us information about our rows, including what type it is. For instance, let's say we want to grab all of our continuous variables. These will typically have a numeric type, like float. Below, I've listed all of the common numeric types, and I'm going to use these in order to select only the numeric column. To do that, I'm going to create a new data frame. I'm going to call it df4_numeric. And I'm going to set it equal to the name of my data frame, .select d types. And inside, I'm going to say include equals num. Num is the list of all of the types that I would like to include. Then I'm going to print it out. And you can see that now I only have the columns that are numeric types. It's dropped things, for instance, like species and island. Another thing we might want to do is grab columns by their name. For instance, if we want every column that starts with the word Bill, we can grab those. I'm going to use a list comprehension. This list comprehension basically says to loop through all of the names in our column names. And if it starts with Bill, make sure you add it to our list. When this is done running, you can see it'll give us a list of column names that start with Bill. We can then use this list to grab those rows from our data frame. There's two ways we can do it. First, we could say df4, the name of our data frame, square bracket, Bill, vars, or we can say df4.loc, square bracket, colon, which is grab all the rows, comma, Bill, vars. When we run this, we can see that we have our entire data frame, so all the rows, but only the two columns that we wanted. As you can see, we can give a data frame a list of columns that it would like to grab instead of a single column name. Now, one last thing we might want to do when we're exploring and cleaning our data is to add a column. For instance, I want to create a new column called bill ratio. That's the ratio of the length and the depth of a penguin's bill. To do that, it's pretty much like adding a key value pair to a dictionary. I'm going to say the name of my data frame, square bracket, the name of the column that I want to add, in this case, bill ratio. Then I'm going to set it equal to df4, square bracket, bill length, divided by df4, square bracket, bill depth, As you can see, if I spell it correctly, what I've done is I've grabbed my two columns and I've divided them by each other. This will create a ratio column. For each entry, it will divide the bill length by the bill depth, and then it will assign that as a new column in our data frame. Once I run this, let's go ahead and check that I added it by just printing out the head of my data frame. I'm going to run this, and then I'm going to scroll over, and you can indeed see my new column, bill ratio. That's all for pandas. Now let's talk about numpy. Numpy stands for numerical Python, and it's a way to implement arrays which aren't available in base Python. Let's explore arrays by comparing them and contrasting them with lists. Here I'm using np.array in order to create an array with the values 1, 2, 3, 4, 5, 6. Then I'm creating a list with those exact same values. Now, one thing that's similar between arrays and lists is indexing. If we want to grab the item at index 2, the way we grab that is exactly the same. For instance, you know from Python that if I say xlist square bracket 2, that's going to grab the number 3. And if I run this, you can see that's exactly what it does. I can also say x square bracket 2, and from my array, it'll grab the item at index 2, aka 3. However, now we're getting into territory where they're different. As you know from Python, if I say xlist times 3, I'm basically going to get 3 copies of the list shoved together in a single list. In other words, for lists in Python, when we multiply, we're doing concatenation. We're basically adding a new copy of the list once per the number we're multiplying by. Arrays work differently. In arrays, when we multiply by a number, we're actually going to multiply each element in the array by that number. So for instance, when I run this, I'm going to get the values 3, 6, 9, etc. Addition also works differently. I'm going to run this cell in order to load in my new array Y and my new list Y list. As you know, when we add two lists together, we basically concatenate them. When I add xlist and ylist and then run this, I'm going to get a single list with all of the elements from X list and all the elements from Y list. However, for arrays, when we add them, it does an element-wise operation. When I add them, it's going to be an element-wise addition. This means the item at index 0 from X and Y will be added together. Then the items at index 1 from X and Y will be added together, etc. So why is this useful? Basically, arrays have vectorized operations that let us apply operations element-wise. And this can be really useful when calculating things like distances. So let's walk through with numpy how to calculate a distance. Remember that this is our distance formula. It's basically for each index, the difference between X and Y at that index, squared, add them all together, and then take the square root. So the first thing that we want to do is get the difference between all of our X's and all of our Y's. Well, we just learned that using arrays, we could just use a minus sign. This will give us the difference between X and Y for every single point. Now that we have those differences, according to our formula, the next thing we need to do is square them. And we can do that here. I'm going to say X minus Y squared. And this is going to apply an element-wise operation to square each of the values in my array. Now that we have all these differences squared, we probably want to take the sum of them. We can do that with a numpy function np.sum. This will take all of the elements in the array and add them together. You can see that we get a sum of 31. Last but not least, I'm going to copy and paste this, and then I'm going to use another numpy function, np.sqrt, which takes the square root. When I apply this, I've done my final step, and I get the distance between my two vectors, x and y. Now, all of that was just to show you how numpy works, but typically we're not going to calculate distances by hand. And since we'll do it a lot in this class, I just want to show you a really quick way. Numpy has a submodule called linalg, short for linear algebra, and it has a function called norm. If we take the norm of the difference between two arrays, it will give us the distance between them. As you can see, we get the exact same number as when we did it by hand. Last but not least, numpy has a bunch of random number generating functions that you'll see from time to time in this class. I'll go over them really quickly. In numpy, there's a submodule called random, and it has a bunch of different functions to generate random numbers according to different distributions. One of the most common would be the normal distribution. The normal distribution needs to be given a mean and a standard deviation to determine its shape. The loc parameter tells you the mean, and the scale parameter tells you the standard deviation. The last argument we're going to add is size, and it tells us how many draws to take or samples to take from that normal distribution. I'll grab 10. When we run this, you can see that we get 10 random numbers, and if you're following along, you'll notice that your numbers are probably different than mine because they're random. Next, we can draw numbers from a uniform distribution where every value is equally as likely. To do that, we can say np.random.uniform. This takes two arguments, low equals 0, high, we'll set that equal to 1, and then size, 10. Low and high are just the bounds of our uniform distribution, the lowest and the highest value we can draw. Again, we can run this and we'll get 10 random numbers between 0 and 1. Again, yours will be different than mine because they're random. The last numpy random function we're going to cover is called choice. We're going to say np.random.choice. And then we're going to give it a list of things to choose from. In this case, it's the list names. When I run this, you can see that it's going to randomly choose a name from my list. Now, this is exciting if I wanted to choose someone to call on in class, but typically how we use this is we're going to use it with replacement. For instance, let's say I want to assign people randomly to groups. I can do that by giving it a list of the groups that I would like to have. Then I can say the number of samples I want to take. And then I'm going to set this argument replace equals true. This says once we grab B from these choices, we're going to put it back so that we could sample it again. When I run this, you can see that we get a sample of A's and B's. Again, yours will look a little different than mine. Now, throughout this whole process, I've been saying that your values are going to look a little different than mine because they're random. But if we want to make sure that we're getting the same values, then we need to set a seed. np.random.seed is a function that allows us to set a seed. And I can use any integer, like 12393. And the idea here is that if you set the exact same seed as me, and then ran the exact same code, like np.random.normal, and we'll say 0, 1, 1, that's going to draw one sample from the standard normal. If I run this and you run this, we'll get the exact same value. You want to use this in any case where it's important that your results are reproducible. That means that you get the exact same values as someone else who's using the same seed. It also means that if you ran this cell over and over, instead of getting a different random number, you would get the same one. That was a lot, but we've covered the basics of both pandas and numpy. I'll see you next time.